We're going to see the relationship between autocorrelation function and power spectral density. As we have seen in the earlier classes, power spectral density is defined as limit t tends to infinity, expectation of square of the Fourier transformed random process by 2 times t. And the power, precisely the average power, can be found from Pxx, and it is 1 by 2 pi integral minus infinity to infinity Sxx of omega d omega. This Sxx of omega is known as the power spectral density, and this is known as the average power, right? Now, in the properties, we have also seen that autocorrelation function and power spectral density are a Fourier transform pair. And in this current lecture, we are going to prove the same, right? So we will start with the inverse Fourier transform of the power spectral density, and then we go forward with it, right? So starting with, let me write the title here for you. Relationship between power spectrum, which is denoted by Sxx of omega, and autocorrelation function. And we are all familiar to this representation. It is Rxx of tau. Right now we'll try to prove this. Okay, when we are starting with it, so we'll start with Sxx of omega, and we have just seen the way in which it is represented. It is limit t tends to infinity, expectation of xt of omega, absolute value of xt of omega whole square by 2t, and we can write this as limit x. Because it has absolute value, we can represent it as xt of omega times xt star of omega by 2t, and xt of omega happens to be Fourier transform of x of t, right? I hope all of you understand that. X of t will have the Fourier transform xt of omega in the range minus t to t. That is what we have seen in the power spectral density in deriving what the power spectral density is, right? So limit t tends to infinity, because it's absolute value of xt of omega whole square, we can write it as a product of the conjugates, right? So we will express x of t as, sorry, xt of omega as integral minus t to t x of t to e power j omega minus j omega t1 dt1, sorry, x of t1 e power minus j omega t1 dt1, and xt star of omega as integral minus t to t x of t2, because it's conjugate, this becomes e power j omega t2 b t2. It can be either ways also. You can suit yourself. This can be t2, this can be t2, this can be t2. Likewise, this can be t1. It's just conjugates, and we are ensuring that there is no lapse in the overlap in the times that we are taking. So let us express this in terms of Fourier transform functions. So starting up, the power spectral density is given as limit t tends to infinity, expectation of 1 by 2t integral minus t to t x of t1 e power j omega t1 dt1. This is the conjugate version, and the other one is integral minus t to t x of t2 e power minus j omega t2 dt2. 1 by 2t is already written there, so we need to be bothered about it. Now I'll reorder integrations as per my convenience. Limit t tends to infinity, 1 by 2t can be pulled out, and the integrations, there's a double integration which goes all the way from minus t to t x of t1 e power j omega t1. Right. What we'll do is, we don't need to waste another step. I can directly write it as exponential because I'm taking the expectation inside. I'll write it as expectation of, sorry, not exponential, expectation x of t1 times expectation of x of t2, and it is e power minus j omega t2 minus t1. This will be dt2 dt1. Right, this is how I have reordered my previous step 2, which is expectation of t1 and expectation of t2. And we very well know that expectation of x of t1 times x of t2 is nothing but our autocorrelation function, which is rxx of t1 comma t2, where minus t is less than t1 and t2, and this is less than t, right? So we shall write as xx of omega. We are reaching to what we have actually stated. So limit t tends to infinity, 1 by 2t integral minus t to t, again an integral minus t to t, rxx of t1 comma t2. These are the variables that we have taken. They can be changed according to our convenience. So dt1, dt2, or dt2, dt1 doesn't really matter because the limits of both t1 and t2 are one and the same, right? So the next step is, we have taken Fourier, we have found out what our power spectral density is. Now, according to our statement, what we have to state is that rxx of tau and sxx of omega are Fourier transform pair. Fourier transform pair. Now for that, we have to take inverse Fourier transform of the power spectral density, and that will be our next step. Please note, this is our power spectral density expression, and we are going to go for an inverse transform for the same. Right, now applying inverse Fourier transform to power spectral density. So what we'll be getting is 1 by 2 pi integral minus infinity to infinity sxx of omega e power minus j omega tau. So that there is no mix up of the variables, let me take it as tau. So there's going to be a bit of change in the variables that I had taken earlier. So integral minus infinity to infinity, I'm going to write the entire expression that we have got here. you can see the expression, the equation 1. I'm going to write the entire equation in the place of Sxx of omega, because that is what we deduced the power spectral density to be. So this is going to be limit t tends to infinity 1 by 2 times t integral minus t to t, and again I'm integral minus t to t rxx of, instead of t1 and t2, I'd like to take it as t and t1 because I have too many expressions there, so I'd like to avoid it. So t1 minus t dt dt1, in place of t2 I have taken as t, so that's the variable I have changed. Okay, dt dt1 and e power j omega tau. I'm sorry, this has to be plus because we are taking inverse Fourier transform, so this will be e power j omega tau d omega, right? So now again we'll go forward and then we will reorder and bring all the exponentials together. We're going to bring all the exponentials together. So I will be pulling out my limit t tends to infinity 1 by 2t over here, and integral minus t to t, integral minus t to t, rxx of t comma t1 e power minus j omega times t1 minus t. Okay, I reckon we should be bringing all the exponentials together, so let's just do it right away rather than taking a couple of steps more. So this will be, you have another integration which is left, so, and also 1 by 2 pi. You must have understood what I'm trying to do here. The minute you see the expression, we should be able to take what we are really trying to do here. dt e omega dt1 and dt. We have all the expressions intact here, and if you see this portion specifically, you will be able to realize that I just want an expression in the time domain, and this is the formula for inverse Fourier transform. And we do have a time shifting property in Fourier transform, which clearly states that if f of t, a function f of t, has a Fourier transform f of omega, right, then the time shifted version f of t minus t naught will have the Fourier transform e power minus j omega t naught, right? E power minus j omega t naught times f of omega. And keeping in mind the time shifting property here, as you can see the expression clearly, e power minus j omega t naught. What we are trying to do over here is literally the inverse Fourier transform of e power minus j omega r t naught is t1 minus t. These two happen to be r t naught. If you just remove this, and our Fourier inverse of e power j omega t1 minus t would be del of tau minus t1, tau minus t1 plus t, because del of t has Fourier transform 1, because del of t has a Fourier transform 1, and if you want the Fourier transform of inverse Fourier transform of Fourier transform of del of t minus t naught, it is e power minus j omega t naught times 1. So here we are actually trying to do inverse Fourier transform of e power minus j omega t naught, which is this one here, and what we get is del of t minus t naught, del of t minus t naught, and that's what we have written here. You can reorder it in whichever way you want, because we know that impulse has even symmetry. our function impulse is even symmetric in nature, right? So let me just rewrite the entire thing for you again in terms of impulses. So this expression that we are seeing in equation 2 is going to change into inverse Fourier transform of omega is equal to 1 by 2 pi integral, sorry, let me just, this is going to be limit t tends to infinity 1 by 2t integral minus t to t. Rather than writing that, let us write the complete expression rather than just writing the inverse Fourier transform. We've got Rxx of t comma t1, and I have reordered the variables in impulse according to the convenience, according to my convenience, right? dt1, dt, dt1, dt. Now this again, I'm going to play a bit with my integrals again. In and out 1 by 2t integral minus t to t Rxx of t comma t1. This is going to be dt, and again after the limit is applied, I'll just let this be here and I'll apply the limit here. So integral minus infinity to infinity del of t1 minus t minus tau dt1. This is the strength of impulse from minus infinity to infinity is going to be 1 according to the impulse properties, or by the virtue of it being impulse. So which leaves us the expression to limit t tends to infinity 1 by 2t integral minus t to t Rxx of t comma t plus tau. Now we all know that autocorrelation function is simply the correlation between two random processes, which are two random variables which differ in time. So the first one is at t and the second one is at t plus tau, a different timings dt. And if we keenly observe this expression, inverse Fourier transform of power spectral density is going to be time average of autocorrelation function. Time average of autocorrelation function. So we can write it as time average of autocorrelation function has the Fourier transform as power spectral density. Power spectral density, and our proof is there. The actual relation between any random process x of t's autocorrelation and power spectral density is the time average of autocorrelation function has the Fourier transform as power spectral density, which is proved quite well. And if x of t, extending the concept, if x of t is at least Wide-sense stationary. At least wide-sense stationary. All of us understand what wide-sense stationarity means. That mean is constant and autocorrelation function is independent of absolute time. So autocorrelation function is equal to Rxx of tau rather than Rxx of t comma t plus tau. Applying the same thing here, considering x of t is a random process, we'd be having the above expression as Rxx of tau having the Fourier transform Sxx of omega. So hence we have proved that the autocorrelation function and power spectral density of a wide-sense stationary random process x of t is a Fourier transform pair. So you'd be wondering if where the time average has gone. So when there is no absolute time, obviously there wouldn't be any time average. So time average also disappears and we are left with Rxx of tau, Sxx of omega. That is the expression we have, and this relation is known as Wiener-Khinchin relation, the relation between autocorrelation and power spectral density, or cross correlation and cross power spectral density being Fourier transform pair, is known as Wiener-Khinchin relations. Wiener-Khinchin relations, a very important aspect and very important thing that we have to remember. So the next video or video lecture is going to be on the relation between cross correlation and cross power density spectrum, and it is obviously evidently it is also, or they are also a Fourier transform pair. The only thing is, in place of a single random process, we're going to have two random processes, right?